Hello everybody, in this new video tutorial we will explain how to communicate our ctrlX code with a Raspberry Pi that has been forgotten at home. The communication will be done using in the ctrlX the Modbus blocks that we have already used in some other tutorials. For the program in the Raspberry, we will use Python and we will show the data sent from the ctrlX core in a LCD. Here we can see how the different elements used come together. Between ctrlX and the Raspberry, we will only use a standard Ethernet cable by using a switch to be able to access the two devices from a single PC. Obviously, it is in the Raspberry Pi where we will have more connection to have to use the LCD. The communication with this element, the LCD, we will done using the A to C bus, which only use two cables for communication, SLC pin 5 and SDA pin 3. I also recommended using the logic level converter when working with different supply voltage, since the Raspberry works with voltage of 3 volts DC and the LCD with supply voltage of 5 volts DC. The logic level converter allows us to work with both voltage in the system but separating both parts through avoiding that we can generate a problem in the devices. The LCD can also be used directly, but it's preferable to use the A to C converter so as not to have to access all the pins of the same, since with the A to C we will only use two communication cables. Raspberry Pi. The first step to activate the entire system is obviously to enable the Raspberry's A to C communication port. This can be done in two ways. First, from the programming console terminal and using the command sudo raspi config. Then select the peripheral configuration option. Choose the A to C option. We will activate the A to C interface. And finally, we should see that the A to C interface activated. The following option of enabling the A to C communication port can be performed from the selection menus. Select the Raspberry Pi icon, choose the Preferences option, and enable the A to C port in the Interfaces menu, then validating the selection with OK. Then we can check if we have already made the electrical connection between the LCD, the logic level converter and the Raspberry, if our Raspberry detects the LCD in the system. We can do this from the terminal using A to C detect -way1. The indicator of our LCD should appear among the list of hexadecimal codes, usually 27, a number that we'll use later in the Python program to access it. The Python program that we will use in the Raspberry is structured in two parts. The first is say the main program, and the second the threads of execution of the program separated into three different parts. Modbus Communication, activation and control function. Extraction of Modbus registers to be sent to LCD. Writing text on the LCD. In the main part of the program, we have first the assignment of the used modules. Library for Modbus Control, module with time-related functions, module used for the creation of the different threads of the programs, library for the LCD configuration. In this last library, we shall verify that the number assigned to the address parameters correspond to the one we have previously located to our LCD, otherwise we shall modify the value. Next, and even within the parts that we call the main program, we have the definition of the global variables. These variables can be used in the different threads of execution, as we will see. The first variable is the rating of the registers from the ctrlX core. The following is the activation bit for sending data to LCD and is used to activate the LCD routines only when the data has been received from Modbus, otherwise errors may occur. The next two lines receive the text structure of each of the two lines of the LCD. The last one is the one that defines the name that we will use of our LCD. I suppose this can be done in many other ways, but it is just one example. As we have already mentioned, the program is divided into different parts: the main program and the three threads of execution. In this part, the different threads of execution of the program are managed. Control thread for Modbus data, control thread for data extraction to LCD, control thread for writing text on the LCD. The first of the functions generated from an execution thread is the control of the Modbus data and works as follows. Assignment of global variables. As we have mentioned before, these variables are defined in the initial part of the program and are linked in the function with the global denominator, allowing them to be used in the way in different functions. Then we use the Modbus module to define the communications IP of the ctrlX core or the devices with which we want to communicate, the port to use, the identification, and if we want the device to perform an auto open. In the next control loop, the data from the Modbus is read. In this example, we are using 225 read registers, which later we will see how it is defined. In any case, these registers from the Modbus are writing to the global variables defined above. Subsequently, the control bit that allows the activation of the rest of the execution threads is activated. In the following image, we can see the relationship of Modbus registers with the characters of each of the two lines of the LCD. To avoid discrepancies in the number of signals, register 85 has been used for the initial character of the first line of the LCD and 105 for the initial character of the second line of the LCD. Both groups have been divided into 20 elements, although the last 4 of each group are not used. Note: it should be noted that we are using the same system used in the other examples, and that in this case, like the others, the register data are used to send data from the ctrlX core and the holding register data to receive the data from the other PLC. The next function is responsible to extracting and structuring the data received from the Modbus and converting them into the lines that we will send to the LCD. First, we have the global variables, as we see among them is the Modbus registers that we were also using in the previous function. In this case, we also have local variables, while allows continuous program execution. The routine itself is only activated if the bit that tells us that we have received data from the Modbus has been activated before. The for instruction allows us to extract one by one the arrived characters and place them in the auxiliary variables. If any generally empty characters of type arrive, it is filed with empty characters. With the join instruction of the string, the recited characters are joined so that the lines to be written of the LC are generated. Applying a minimum time interval for text to appear on the LCD while clearing witness lines. The last of the functions is the one that will write the line generated in the LCD. We also have in the first place the global variables. We will use two auxiliary variables to verify that a new text has arrived. The while, as we have seen above, always remain active, and the rest of the instruction will only be executed when data has been received from the Modbus. In the if new text are checked, that next the new text has been received. LCD is cleared with the clear command, and the value of the auxiliary line are updated that allows us to insert the arrival of a new text. This is done analogously in both if extrusions, so that the both lines are updated. Finally, the lines are written with the new text on the LCD. This is the structure of operation of the system. Considering that I am not an expert in Python, and that certain rules must be followed so that errors do not appear in the compilation. As already mentioned, the structure is as follows: module import, defining global variables, definition of the functions used, control of program threads, main program. As a rule, the function must be previously generated before being called, or otherwise errors such as those observed in the image appears. PLC program in ctrlX core. This is the structure used in the ctrlX PLC program, considering that it has been used as a base, which had already been used in some other tutorials in which Modbus has been used. For the operation of the system, we have two main folders: Prog 070 for Modbus Communication with Raspberry, and Prog 71 for sending the data of the LCD format by the sequence of operation and sending the text. As we have mentioned in the Prog 070, we control the Modbus Communication. In the first point, we structure the communication data, as I say, following the pattern of other manuals dedicated to the Modbus and establishing the communication areas that we are going to use. Remember, register data for the data sent from the ctrlX core, like server, and the holding register data that will serve as data reception, although this data can be used in both directions and therefore as a read or write. When using the structure used in other manuals, we should practically not do anything in the way of managing Modbus Communication. The variables are coil data and are input data, although they are not being used in any of the cases. If we must have them declared, since they must be included as data in the Modbus Control module. The module structure starts with the module with a general name and includes calls to the other modules in the group. The Modbus Control module is used as a server and must be configured with the structure that we have previously declared. In this way, the system is permanently analyzing the Modbus data so that the rest of the devices can collect or send the information that is necessary for operation. There is also a control system for the automatic reset of the module in case of error or fixed connection, so that the connection is always active. In the following folder, the control modules for the control of the text sent to the LCD via Modbus are managed. First, we have the variables of global type that we are going to use for the control of the text. We can also see how the characters of both lines of the LCD are assigned from the defined array. There is a tendency of many occasions to start the arrays by the array number 1, ignoring and leaving out the 0. However, assigns this can also in many cases generate a problem. I always prefer to start with the 0 although, as in this case, I not use it sensitive if the variable as initialized. On the 0 array and this does not exist, we will generate array error because this does not exist. The characters for each of the lines therefore appears from array 1 to array 16. As in the other program group, the first module makes the call to the rest of the modules in the group. The sequence itself is extremely simple, and in it we manage the text we want to appear on the LCD. Obviously, it is just an example. The steps, 6 in total, are controlled by a case, and the change of steps is made by a timer that we will manage outside the case, so as not to cause a freezing of the same, and that will be activated when the step is active. If we want to modify the speed of change of the text, we can change the value of the timing, so that the text changes fast or less quickly. The last of the modules is responsible for managing the sending of text to the two lines of the LCD. For this, we use a for that allows us to extract character by character the string received from each of the lines and send each of them to each corresponding register. If you look at the number in the Modbus register used, they start with 84 and 104, and although this is correct, the sum of the variable a of the instruction for adjusts the value to the registers that we had previously defined, starting line 1 in register 85 and line 2 in register 105. Of course, this is just a small example of using two devices such as ctrlX core and Raspberry, and that also helps us to see how the Python program works. Thank you for your attention.